Thank you. It's really nice to be here. So I'm going to focus on sea level rise, and really sort of wanted to try to do two things. One, just sort of cover some of the interesting ground about the relationship between climate change and sea level rise. Some of that's kind of for your edification, but then also go over some of what we're developing as part of an in-process updated assessment for Washington State that is focused on sea level rise. So the other title you could give to the talk is Why Antarctica Should Matter to You, and we'll cover that ground in a few different places. So first, before I get there, just a little bit more of introduction. Should you be unfamiliar with what Sea Grant is or not have heard of it before, really I see us as every coastal state has a Sea Grant program. We're University of Washington based, and really I see us as trying to make this connection between science, sort of ivory tower, sort of generalized science kind of idea, and communities. In my case, coastal communities who can use science to help manage various problems. I work in the area of coastal hazards, but a lot of our folks work in water quality and fisheries and that kind of thing. And then the reason I'm here, I started working for Sea Grant about 5 years ago. I come from, my research background is in coastal geomorphology and coastal oceanography. And pretty quickly after starting with Sea Grant, I started to get wrapped up in these very localized climate change assessments. There's a lot of interest in trying to understand what does climate change mean for us, whether that us is a institution like the Olympic Coast National Marine Sanctuary, which I helped with the climate change assessment for, or the Jamestown Sklallam Tribe. And these are a couple examples of these kind of local scale climate change assessments that we got involved with. One for the North Olympic Peninsula, sort of a multi-entity, multi-county, multi-city, multi-tribe process, and then one for Island County. So what we're trying to do now is take some of the methods that we developed as part of these very local scale processes and apply them statewide. So some of this kind of sea level rise updated assessment stuff that I'm going to show you is developed from these very sort of local scale assessments that I was involved in. And this Washington state-wide updated sea level rise assessment is part of what we call the Washington Coastal Resilience Project. It is a multi-partner project focused on trying to build sea level rise resilience into community planning in Washington State. It's got a variety of different objectives sort of outlined in these bullets, which you may or may not be able to read if you're in the back. The one in red is the one that I'm going to focus on today, and the objective that I'm leading, which is to support an updated sea level rise and storm surge assessment for coastal Washington. A lot of the other bullets are really focused on how you take that information and try to integrate it into planning, and that's really the harder part of the sea level rise work that we have to do in Washington State. So I like to start by blaming these guys for us being gathered together today, maybe. So I like to blame these guys for climate change and by extension for sea level rise. Some of you may recognize these fine-looking gentlemen. John Tyndall published a paper in 1864. He's the guy closer to me. Published a paper in 1864. He was a chemist, and he was interested in the properties of substances. And one of the things that he investigated were properties of carbon dioxide gas. And he found that if you pass heat energy through that gas, not as much comes out as you put in. So it absorbed some of that heat energy. He wrote a paper about it, published it. It languished for 30 years, but then it was picked up by Svante Arrhenius, who made what I view as sort of the leap that we now view as our sort of climate change conceptual model. And he said, well, hey, if this property of this gas that John pointed out is correct, and we pump enough carbon dioxide gas into the atmosphere, we can warm things up. We'll absorb some of that heat energy that radiates off the Earth, and we'll be able to warm up the atmosphere. He was writing from Denmark, and he thought it would be a really good thing to have that happen. He saw it as a boon for agriculture and things like that. But he's really the one that made the leap and did the calculations to show that this sort of property of this gas and other greenhouse gas, what we now refer to as greenhouse gases, could be connected on a larger scale to our environment. And this is our sort of basic conceptual model for climate change. Many of you are probably very familiar with this, but closer to me over here is our sort of balanced global energy budget depiction, where you have light energy coming into the Earth system, warming up the mass of the Earth, which then re-radiates heat energy, some of which escapes back out to space. If those two arrows, what comes in and what goes out, are roughly equal, then we have a balanced energy budget. The notion behind climate change is that we are toying with that heat energy arrow by adding long-lived greenhouse gases to the atmosphere that are slowly retaining more energy in the Earth system. So this is kind of our fundamental conceptual model for climate change. So let's start connecting that to the ocean more specifically. And we can do that using this very tiny equation at the bottom, which maybe you can't see in the back, but for those of you that can see it, hopefully you recognize it, because this is something you probably picked up in your high school physics class. This is the heat flux equation, and it very simply allows us to connect changes in energy or energy fluxes to changes in temperature in a substance if we know their mass and we know the specific heat of a substance, which is kind of a fixed property of a substance that tells us how much we expect it to warm up or cool down given a unit change in energy. So you can go onto Google and look up the mass of the atmosphere and the specific heat of air. And there are people smarter than I that have figured out how much extra energy we've retained in the Earth system over the past, say, 5 or 6 decades. And if you go through this process, this very simple equation, which I will not force you to do, but if you do this and plug in the mass of the atmosphere, specific heat of air, and you have that change of energy, and you calculate an expected change in temperature for the atmosphere for the last 60 years, you come up with a number that's on the order of about 70 degrees Celsius. That's the expected change in temperature given the amount of energy that we've retained in the Earth system. 70 degrees Celsius. So has temperature changed that much? No, of course not. So why is that? Well, it's because the ocean is sucking up the vast amount of that heat energy. This time series is intended to, this is an estimate of the global energy budget over about the last 60 years or so. This is change in total heat content. It's measured in joules since 1961, and the blue line is the ocean component, and the red line is the land and atmosphere and ice melting component. So hopefully what jumps out at you here is that the ocean is just sucking up the vast amount of this energy. And the cool thing about the ocean doing this is that it has a larger mass than the atmosphere, and also the specific heat of water is quite a bit larger. So it takes more energy to warm up a unit mass of water as compared to a unit mass of air. So the ocean can do this while heating up almost, actually increasing temperature almost imperceptibly. But that heat does matter, and it matters in 2 ways in regards, in particular, to sea level rise. And these 2 processes driven by heat are things that we tend to be very comfortable with. One, if we expose ice to heat, it melts. So we all sort of experience this on a day-to-day basis. And the other thing is that if we warm water up, it expands, right? So I've got a picture of a hot water heater there because our hot water heaters in our house have an expansion tank meant to account for this process so we don't continuously spill water on our floors as we heat it up. And in fact, if we look at a record of observed global average sea level, we see these 2 processes at play in what we observe over about a 10-year period. This covers about 2005 to 2014. This is global mean sea level change. This is measured in millimeters. So this scale in total is about 1 inch or so. And the 4 lines on here, the bottom blue line is an estimate derived from autonomous temperature measurements from all over the ocean of this expansion effect on the ocean, what we call the steric component to sea level change. So this is an estimate for the steric contribution based on ocean temperature measurements. The red line is an estimate of the amount of new mass added to the ocean. So when ice melts, it adds new mass to the oceans. And this is a satellite-derived estimate of that change in mass, the red line. If we add the blue line and the red line together, we get the purple line. And then the black line there is an independently derived estimate of average sea level surface in the oceans that's derived from satellite altimetry, so an independent estimate. So what we would expect to see is the purple line aligning fairly closely with the black line. And in fact, that's what we do see. And it suggests that these two processes are really driving observed sea level change globally. This is also the game for deriving sea level rise projections, is you take each of the inputs into a global sea level, try to estimate how they respond to heat and to emission scenarios, and then sum them all up to come up with sea level rise projections. So here, we've got 4 components outlined here. They are Greenland, Antarctica, mountain glaciers, and then that thermal expansion or steric component. And the game for each of those becomes, how do we expect each of these to respond to heat associated with different emission scenarios, and then we add them all together. And what we typically end up with is a curve, sort of like what's shown here, where you have time along the bottom axis, and then you've got some distance unit along the y-axis. This is shown in both meters and feet. And in this particular case, there's 3 different blue polygons shown, just sort of showing different methods for going out about this process of projecting sea level rise. And the thing that I want you to note there, especially as we move out in time with these projections, is we often see a lot of uncertainty in these projections. We see big ranges. In this particular case, we have about a ½ foot to over 6 feet as displayed here. Now let me also clarify one thing that I think is important here. So if you note the sort of ice components here, these masses of ice are all land-grounded ice. So for sea level rise projections, we don't necessarily care about the sea ice component. And let me sort of try to use a demonstration to clarify why that is. This is where I usually also make a big mess. So what I've got going on here are 2 different ocean systems. And this particular, and it's kind of hard to see the water level because my coloring didn't really make it through the water, but we'll do our best here. This one's a little bit better. Okay, so this is going to be an ocean system. I've got an ocean basin here with a set water level in it. And to that ocean system, I'm going to add some sea ice. So I'm just going to throw it in here. And then I'm going to use this piece of paper to mark the ocean level associated with that global system. In this particular ocean system, my ice is going to be land grounded. So I've got my ice on a continent here. And then I'm going to move, my paper's getting a little wrinkled here. But I'm going to move that paper up to mark the ocean level. And basically for the remainder of sort of the talk, as these 2 masses of ice melt, we're going to get to observe which of these systems changes sea level in these 2 ocean systems. So once you sort of think about it this way, you start to see that this sea ice system, as it melts, this ice is already displacing water. So as it melts, you wouldn't expect the level of the ocean in this system to change. Whereas over here, this is adding new mass to that ocean basin. So this is where we would expect to see sea level change. So I bring this up only because this is kind of a confusing point sometimes and misinterpreted in the media about the role that sea ice plays in driving sea level change. And so sometimes you'll see articles about sea ice and its relationship to sea level rise. Well, that's kind of a spurious connection. Sea ice is an important climate change metric, and it's tracked very carefully because of that, but it doesn't have a direct connection to sea level change. So in this particular case, again, we're focused on these large masses of land-grounded ice and their contributions of new mass to the ocean basins. Okay, so let's get back to that first issue associated with uncertainty in sea level rise projections. This is a characteristic of a lot of climate projections, or a lot of projections for a lot of parameters for that matter, is uncertainty into the future. And this has been a factor in some of our very local sea level rise assessments. This is one of the first ones that was focused on the state of Washington. It's about 10 years old at this point. And the only thing I want to emphasize here is that they created this summary figure, which you probably can't see, but essentially they provided two different date steps, 2050 and 2100, and they provided a best estimate for expected sea level change in Washington state at those two date steps, and then they have these kind of large bars representing possible ranges. The issue that possibly you run into here from a planning standpoint is that it may be hard to make a decision within this range about what you plan for. And obviously 6 inches by 2100 means something very different as compared to, in this case, 50 inches of sea level change by 2100. So where do you plan for in that range is a potential shortcoming associated with this kind of communication. Now, this was 10 years ago. We're taking advantage of some new tools to try to do this a little differently. So what we're doing in this updated assessment that I referenced is taking advantage of some recently published work by a team out of Rutgers University, which have attempted to take each of those components of sea level change, they're arrayed across the top here, Greenland, glaciers and ice caps, thermal expansion, and the contributions from Antarctica, and come up with for each of them, they come up with a likelihood or probability distribution of their contributions given a certain emission scenario. That's represented by these lines in each of these graphs, where these different lines refer to different levels of probability or different likelihoods based on what we understand about how these different systems respond to heat energy. So where you see these lines kind of mushed together, closer together, it suggests that we feel comfortable about what we know about, in this case, how glaciers and ice caps respond to a particular emission scenario and a particular heat scenario. Whereas if you look over at Antarctica, if you can see those lines, they diverge quite dramatically. And that suggests a large degree of uncertainty about how that component plays out over time. So we don't know a lot about how these big masses of ice melt, is essentially what that's conveying. But if you combine those uncertainties, you can create a single probabilistic communication format or likelihood-based format for communicating within the overall range of possible sea level change. So that's what we're attempting to do here in this figure, where you've got time along the bottom again. You've got a distance axis over here. This is in feet, relative essentially to the present. And the legend, which you can hopefully see, essentially each of those lines has a different probability or likelihood associated with it. So we haven't really affected the range here. We still have large uncertainty regarding future sea level. But we've provided a tool for potentially assessing costs and benefits or different levels of risk tolerance associated with different decisions within that large range, sort of a best estimate of likelihood based on what we currently know effectively. So it's also worth noting that there is uncertainty due to future emissions as well. Global climate modeling makes use of these representative concentration pathways. They're called RCPs. In this case, represented by these 4 different lines related to future carbon dioxide concentration. RCPA 0.5 is the higher emission scenario, and then you go all the way down here to this low emission scenario of RCP 2.6. And if we translate those into sea level rise projections, which is attempted in this summary table, in this case you've got 3 different date steps, 2050, 2100, and 2150, and within each of those 4 different emission scenarios is summarized. Don't pay attention to any of this. Just focus on this best estimate projection for each of those 4 emission scenarios for any particular date step. And really the thing to sort of point out here is that in fact with sea level rise, we don't see a whole huge amount of variation between emission scenarios in terms of future sea level. There is a little bit, right? So this is where what we call mitigation, the reduction of greenhouse gases, matters for this climate impact. But almost regardless of what emission scenario we end up following, this suggests maybe that sea level rise planning is still something that we should be doing. We still expect impacts even at our lowest emission scenario, RCP 2.6. All right, let's start turning our attention away from the global and start to get regional. So this is a altimetry-based, so a satellite-derived average global sea level pattern dating back to about 1992, so covering about a 30-year period. This trend line here is on the order of about 3 millimeters per year, so that roughly equates to about 10 inches per century or so. This is commonly cited as our current kind of global average rate of sea level change. This particular curve, if you break it down globally, which is what this map is intended to do, you actually see there's a lot of spatial variation to this pattern. So there are places on this map that are these warmer colors, and those relate to these rates along the bottom. So the warmer the color, the higher the rate of sea level rise, and the cooler colors relate to lower rates or even sea level fall in some cases. And there's considerable variation. These parts of the Pacific are seeing rates of sea level rise that are many times the global average, where there are places on the globe where sea level is falling, like down here by Antarctica. This map suggests that we live in an area where over this time frame, we've actually seen something sort of closer to zero in terms of our, what we call our absolute sea level change rate. So what's going on here? Well, there's probably a couple things going on, but certainly we have to try to take this into account when we're projecting sort of a regional sea level, expected sea level. So one of the things that's going on here, and this kind of gets into this like interesting process territory, right? So is what we call sea level fingerprints. And I sort of think of this as ice hugging the ocean. And the notion here is that for these large masses of ice that we're interested in their contributions to the ocean, though masses of those chunks of ice are so huge that they actually exert a gravitational influence on the ocean, on the global ocean, as they melt, and that mass relationship changes, gravity is a function of mass, as that mass relationship changes, the distribution of water around the globe actually changes as well. So it's kind of a baffling thing to try to wrap your head around, but it's important in terms of expected future sea level in our neck of the woods. So this particular map is intended to convey what you would expect to see at any particular location in the globe if you melted the equivalent of 1 inch of global average sea level off of Antarctica. And so this scale over here ranges from negative 0.4 to 1.2. And you'll notice that right around Antarctica, if you melt that 1 inch of water off of that mass of ice, you actually expect to see sea level fall directly near Antarctica. Whereas if you look at our neck of the woods, a little further from Antarctica, we expect to see more than 1 inch of sea level rise in our neck of the woods. So this is another reason why Antarctica is really important for us. One, it's potentially a massive contributor to sea level change, but also if Antarctica melts, we see more of it than other places on the globe. If we look at other sources of ice, like Greenland, we see a different pattern. So this is the same map, same exact scale, but melting from Greenland. And you'll note here that Greenland, near Greenland, experiences sea level fall, whereas places further from Greenland in the southern hemisphere experience more than 1 inch of sea level change. So where the melt comes from matters to us, essentially. And we are influenced more dramatically by melt from Antarctica than melt from Greenland. And this leads to best estimates, if you will, of projected sea level that look something like this. So these are 3 different time steps, 2030, 2050, and 2100, and these are sort of best estimates of sea level change by those 3 time steps for, in this case, the Strait of Juan de Fuca, SJDF, and global. And you'll notice in each of these cases for the Strait, the best estimates are lower than the global. And that's due to this sea level fingerprinting influence. Now, the assumption embedded into these best estimate projections is that Antarctica doesn't actually contribute that much. That's been sort of a feature of previous sea level rise assessments. But as we learn about the possibilities of Antarctica contributing, in particular if it does contribute a lot more, this relationship between the global and the local sea level pattern changes for us. So Antarctica matters. All right, let's get even more local and start to think about what we call relative sea level. This is a schematic of a tide gauge. We are very fortunate in Washington State to have a large network of tide gauge. We have about 8 in our state. And tide gauges measure what we call relative sea level. So here, they're attached to the land. So the water level measured by the tide gauge is actually a function of both what's going on with the ocean, what we call absolute sea level, and what's going on with the land, what we call vertical land movement. So you can think of that relationship as relative sea level equals absolute sea level plus vertical land movement. What we're interested in terms of from a community planning standpoint is relative sea level projections, right? This is what we see at a particular community. So that suggests that we also have to resolve this vertical land movement thing in order to understand as credibly as we can the expected impacts in a particular community. And we can see this in observed water level patterns from Washington State. These two plots are taken from the NOAA Tides and Currents website. This is where NOAA serves their tide gauge data. And this is the long-term monthly average water level record from Seattle. And this is the same from Neah Bay. This one dates back to 1898. Might be 1895, one of those. This, the Neah Bay gauge dates back to 1937. So these are our 2 longest water level records in the state. And you notice 2 totally different things going on here. In Seattle, sea level is rising. If you didn't know that, sorry to break it to you. It is happening. So sea level rising at a rate of about 2 millimeters per year, roughly 7 to 8 inches over a century, something like that. In Neah Bay, relative sea level is falling at a roughly equivalent but opposite rate. And these 2 patterns are driven by differences primarily by differences in vertical land movements between these 2 communities, which really aren't very far from each other. 60 miles as the crow flies or something like that. So when we go about the process of trying to develop these localized or relative sea level projections, we take this into account. This is an example from the project that I mentioned from the Olympic Peninsula, where we used data from tide gauges, which are represented by these black squares, and data from GPS stations, these continuous GPS stations, here represented by these circles. These are stations that are scattered around the landscape. Most of them were originally installed in the mid-90s, early 2000s, primarily to try to measure horizontal movements of the land to understand tectonic forcing. But we're starting to be able to resolve vertical movements from them. They've been in place long enough. And this is those data on uplift or subsidence translated along this transect stretching from Neah Bay sort of towards central Puget Sound. And in this case, uplift is above that line there, which you might not be able to see in the back. Subsidence is this part of the scale down here. And you'll notice a gradient from Neah Bay in towards Seattle. Where Neah Bay experiences uplift, we estimate on the order of about 3 millimeters per year, whereas these areas, Port Townsend and Seattle, are probably experiencing subsidence on the order of about 1 millimeter per year, roughly 3 to 4 inches over a century or something like that. So these rates are pretty small compared to future projected sea level change rates, but they do influence projections, and they actually also influence, obviously, what communities have already observed and experienced. This is how they play out in projections. This is for the 3 different communities, Neah Bay, Port Angeles, and Port Townsend, stretched across the Strait of Juan de Fuca. And this is a projection table. We've got 3 different time steps. We've got multiple likelihoods or probabilities, but I want you just to focus on the best estimate for 2050 for each of those communities, which I've circled in red. These are in feet relative to present. And for Neah Bay, we come up with a best estimate by 2050 of 0.3 feet. For Port Angeles, 0.6 feet. And for Neah Bay, 0.9 feet, right? So that's the influence of vertical land movement in the community's relative sea level projections. Not huge, But it matters to a degree in terms of how they interpret their vulnerability, and certainly in terms of the timeline at which they would expect to start to see impacts associated with sea level change. So you can also combine these two sorts of information, the likelihood-based probabilistic projections with that vertical land movement information to come up with these localized projections, and you can map them on the landscape. This is mapped onto the Dungeness River Delta, which some of you may be familiar with if you've been to Dungeness Spit, for example. It sits right over here on this map. This is the river delta adjacent to the Spit. This is the mouth of the river. And like a lot of low elevation landscapes in Puget Sound, there's kind of a fronting berm along this delta that's been heavily developed. So there's a lot of homes along here. And this is one of our more vulnerable areas on the Strait of Juan de Fuca in regards to sea level change. But what you can do here is these different shades of blue are related to different likelihoods of sea level inundation, in this case by 2050, on this landscape. And so sort of the idea is you can start to use these different shades to understand potentially different places, the likelihood of impact in these different zones, potentially prioritize planning actions or other sorts of actions associated with increasing resilience on this landscape. So it's worth noting that our current best available science, one of the reasons that we were motivated to do this updated assessment is our current best available science, which is the National Academies of Science 2012 report on sea level rise for Oregon, California, and Washington. You really can't see it in this table, you have to take my word for it, but they applied a single vertical land movement estimate across sort of the entirety of Oregon and Washington. Whereas in fact, we have a large degree of variability that may matter, especially in terms of community credibility and making sure that you're providing the most localized information possible. So for our statewide project, we kicked off an updated vertical land movement assessment that focused on the entire coast of Washington. This is kind of a preliminary product from that assessment. It includes, in this case, 4 different data sources. So each of these dots, which you may be able to see in this landscape, are different point estimates of vertical land movement that are derived either from these continuous GPS stations, which look like this one, or tide gauges, or if you can see, there are some of these dots that are arrayed really closely together that follow the path of highways. These are actually monuments, Department of Transportation monuments that they use for engineering that can be resurveyed, so you can come up with an estimate of vertical movement at each of those monuments. So those are built in there. And then in this case, we also have employed these kind of evenly spaced dots that you see sort of throughout the landscape are actually derived from a tectonic locking model, a model of how we expect the landscape to deform due to tectonic forces. So those are all combined together to come up with this heat map that you see here, where in this case, red colors are uplift, cool colors are subsidence. The scale goes from about 3 millimeters per year to negative 3 millimeters per year. So roughly, 9 to 10 inches per century, either upwards or downwards. And you'll note there are some sort of clear spatial patterns, certainly from the coast into the sound. We see a gradient from generally uplift to subsidence. And then if you go from south to north, you also see a gradient from subsidence to uplift as you move up towards Bellingham. So anyway, we'll plan on sort of building that into relative projections that are intended to be used at the local scale around Puget Sound and the coast of Washington. So the final thing I wanted to mention is that the impacts of sea level rise really aren't observed in the average. They're observed more in the extremes. How do they contribute to extreme events that we already experience, right? For us in Puget Sound, those tend to be wintertime events. They tend to be when we have a high tide that coincides with a low pressure event. We might have some wind and waves on there to drive flooding in the near coastal environment. This photo is from Alki, December 2012, when the water level as measured by the Seattle tide gauge matched the previous record from 1983. This particular event was almost entirely high tide and pressure driven. There's really not too much of a wave driven component there, but waves do play a role as well in Puget Sound driving flooding. So to try to address this, we went about a process. This is a process we came up with for Island County, We're going to hopefully do something like this statewide, although it's not yet abundantly clear how we're going to do that, in which we went back to the tide gauges. Again, we're very fortunate to have this tide gauge information from Washington State. And from that, we extracted the highest water level measured in every year, in this case from 4 tide gauges around Island County: Port Townsend, Seattle, Cherry Point, and Friday Harbor. We said, what's the highest water level measured in that year? These are time series of those from each tide gauge, but they can be translated into a distribution. So we end up with a histogram of water level. This is in meters above mean high or high water. It varies from about 0.2 or just shy of a foot to up towards 1 meter. So a little 3+ feet or so of basically sort of what do you expect in a given year for your highest water level. And when you take a look at that histogram, you'll notice there's a curve to it or a shape, which tells us something about what we can expect or what the likelihood of an event is in any given year. So we said to ourselves, hey, well, we have a likelihood of a sort of an extreme water level going into any given year. We can combine that directly with our likelihoods of sea level rise to essentially come up with a likelihood framework for extreme water level events as well, which may be more useful or just another tool for planning, because it tells us maybe something about what to expect in the future for extreme events. Different kind of impact. Sea level rise projections tell us something about daily inundation. This tells us something about maybe your once or twice a year event. And we can put them in sort of in exactly the same framework. We've got time here, we've got likelihoods associated with them, and just like that sea level rise information, we can also map them. This is for Port Townsend, which you may recognize, and there are 2 maps here. There's the sea level rise map for 2050, and then there's that annual extreme water level event for 2050. For the sea level rise map, if you can sort of see that map and you know the terrain roughly, this is downtown Port Townsend. This is Fort Worden right here. You can see that there's little suggested in the way of sea level rise vulnerabilities from that average, from that mean high or high water translation, or the average sea level. But extreme water level events, there is vulnerability that emerges, and you can compare this with something like a contemporary flood map to understand new places that may be vulnerable on the landscape, new infrastructure that may be vulnerable, that sort of thing. For those of you that know Port Townsend, there's vulnerabilities up at Point Wilson. This is the Point Hudson area. There's a little marina there. And then the Katai Lagoon and also the Boat Haven area of Port Townsend all emerge as vulnerable. Some of these are currently vulnerable to flooding. We see little increases in the likelihood that they'll be flooded or new areas that are vulnerable. So, thank you so much for your attention. And I think we have a little bit of time. Thank you. Yeah.
I have a question about the inundation maps that you showed.
Yeah.
Are they taking into account storm surge events, or is that something that would be additional?
This one is. So this one's intended to get at mean sea level change. We sort of say the way that we map this is we use current mean high or high water. And so what we're getting at here is translation of that mean high or high water line on the existing landscape. This one builds in that likelihood of those extreme events, which are driven in part by storm surge. And so that's what this is intended to get at. And you know, if we had, so this is 2050, if we had this same map for 2100, that's where, you know, comparing the two, you really start to see where do your new vulnerabilities emerge? Where are places that are not currently mapped as vulnerable? Where do they become vulnerable? That kind of thing, to those kind of once or twice a year events. Yep.
Yeah, as for what went into these maps, the histogram, can you just go back to that?
Yeah.
And say how you translated the 4 gauges into that?
Yeah, so in this particular case, what we did, and there's a variety of ways of going about this, but we essentially took the entire record for each of these 4 tide gauges and extracted the highest water level measured in any given year, well, in every year of the record. So this time scale here goes back to 1898 because our oldest record that we used was Seattle. And then you can see that most of these records are considerably shorter. Friday Harbor and Cherry Point both date to the mid-1970s or so. But from each of those, we're pulling that highest water level and then just combining them all into a histogram. So this tells us, what we can expect on average in any given year. This down here says 0.6. This is in meters relative to mean high water. So this would translate to about 2 feet, right? So it says going into any given year, or really we mean winter, because that's when these events occur, we expect to see a water level event most years that hits 2 feet above mean high water. On the boundary of the distribution, we get up towards a meter, right? 3.1 feet is generally sort of our extreme still water level, at least based on our historic record. So that's kind of our extreme event. Now, this is based off tide gauge data. This does not include waves. Tide gauges do not measure waves. So this is what we call still water level. But this tells us, on the extreme, maybe once every 100 years, or we can sort of translate it into a return frequency, we expect an event that gets 3.1 feet above mean high water. So this gives us effectively a likelihood distribution going into any given year. And what we've done here is we've combined our sort of uncertainties associated with sea level rise with those uncertainties associated with extreme events to come up with a likelihood distribution for that annual extreme water level.
So that map, the map we were just talking about,
Yep.
It's using tide data from not just around Port Townsend.
This one, let's see. So this particular map, because actually what I showed you there was from the analysis for Island County. This one I think we used multiple gauges to characterize the storm surge patterns here too, although I can't remember exactly which ones. Port Townsend does have a tide gauge, but it's a little bit of a shorter record. So we may have used other gauges there to sort of bulk up that record a little bit,
Thank you.
if that makes sense.
Yeah.
Yep.
Obviously, Antarctica's way bigger than Greenland, but Greenland's still pretty huge.
Yes.
And when you showed that,
And I don't want to imply that it doesn't matter.
right.
Right.
Well, so my question was, way back early, you
Yeah.
talked about the different potential future outcomes, and for Greenland, they're all a positive contribution. For Antarctica, they diverge. And I'm just curious why there's so much more uncertainty about Antarctica.
It's a good question. I don't necessarily know all of the details, and there are, Jim or Guillaume or Laura, there's people in the room that may. But, my understanding is that built into some of the assumptions about Antarctica that aren't necessarily built into or don't play as big a role in projections for Greenland is the notion of a feedback. So some climate models suggest that associated with climate change will be increased precipitation in Antarctica, and even though it may be warming, it's still really cold. And so that precipitation will actually act as sort of a positive feedback and add mass to it, kind of even as it's melting at the fringes. So, one thing that characterizes the best estimate is the dark line here, and the best estimate, this is to 2100, is essentially for zero contribution to sea level change based on this model, but with large uncertainties, right? And these, it's these uncertainties in Antarctica and to a lesser extent Greenland that really drive these tails of this distribution here, right? That give us these projections like 8+ feet, for our neck of the woods by 2100. That's really driven by some of the extremes from Antarctica in particular.
Can I add?
Absolutely. This is Guillaume Mauger.
So it is also the case. Stand up. It is also the case that Greenland is simpler than Antarctica, just topographically for one thing. So it's just much more straightforward to sort of envision how the glaciers and then also model how they would come out. So that's one piece. The other piece is that the weather of Antarctica is distinct. Greenland's a lot more just subject to actually the North Pole in general is warming and expected to warm at a much faster rate than the South Pole. And because there's an ocean all the way around Antarctica, the weather there is a lot harder to capture. It's also more isolated from the warming that we're seeing elsewhere in the globe. So it's sort of a different piece of that.
Yeah.
So you've been talking about sea
wondering how the reflectivity of sea ice played into the thermal expansion.
That is a good question, and one that I think, again, since Guillaume's here, and he's much more familiar with sort of the global climate modeling world than I am. Can I defer that one to you?
So,
Thank you.
How are you thinking the reflectivity of sea ice would affect?
Well,
thermal
I
expansion?
mean, ice reflects light better, and as you are.
I see what you're saying. Yeah. So as you melt back ice, you're exposing to darker oceans, so
Yeah.
there's more sunlight. Yeah. I wish I could do better than Ian on this, but I don't.
I would just lie about it.
I don't
So.
know. I mean, the models do include sea ice models, right? So when they're modeling climate and warming over the long term, and they're going to include things like the albedo in their, energy budget calculation. So presumably the models that they're capturing sea ice right are doing that.
It
But
just
I don't
seems like
actually know.
more and more of the Arctic is actually becoming clear.
Well, certainly things, like some of the observed trends from the Arctic are noticeable.
So that's a little bit less straightforward though, because one of the things that sea ice does that's really effective for transmitting heat in the ocean is that it makes the top waters a lot more dense. When you make sea ice, it's mostly just water, not salt water. So you're outputting really cold and also really saline water that sinks to the bottom and makes it mix. So getting the whole ocean to heat actually happens better when you're creating a lot of sea ice. When you don't do that, there are concerns that you actually cap the ocean with a warm layer that doesn't mix, and so you're limiting the amount of heat. The models are supposed to capture all those things, that and what you're describing, and I just don't know what the sort of balance is.
And it's worth noting that some of these distributions that are employed in this model that we're utilizing for thermal expansion are derived from global climate models. So, to the degree that they're taking account of all these processes, that's where those projections are coming from. Yeah.
Does this framework include the uncertainty about what RCP will follow, or is there one of these for each?
Great point. It does not. These are sort of associated with an emission scenario. This one is for RCP 8.5. And largely sort of what we visualized is RCP 8.5, but that table that I showed somewhere along the line, attempts to convey the differences based on those different emission scenarios. But yeah, that uncertainty is conditional upon your sort of chosen emission scenario. Yep.
Have any of the counties that you have done this work for taken it a step further from assumed impacts on other structures to actually changing their current land use regulations to anticipate and actually do something real versus sort of?
So there have been some small examples, nothing dramatic. So I tend to work in these kind of more rural communities and counties, and we've seen instances like the Jamestown tribe, for example, fairly quickly translated some of their impact information into decisions about development. They had some proposed shorefront developments that they decided to defer. Not defer, they decided not to do them. So in the case of like Clallam and Jefferson counties, we haven't seen yet translation into some of their required planning processes like comp planning or shoreline master planning. But we have seen things like Clallam County, as a consequence of our work there, the county commission adopted a resolution that required each of the county departments to build climate planning into their budgets, right? So a little step, hopefully, towards building this into something like a comprehensive plan.
You also implied that some of this work might happen at the state or larger level than what was done.
Yep.
What is the likelihood of that and when?
So I hope I can say the likelihood is 100%. We are in the process of doing it. That project sort of officially concludes May of 2019. Some of what you're seeing here, like this summary table, are taken from a draft document that we're hoping to sort of have out soonish, like within months, I hope, maybe less. One of the things we intend to create, though, are these kind of what I'm sort of currently referring to as localized appendices these just sort of smaller summary sheets that would be appropriate for use at a community scale that would have relative sea level projections, some sort of information about impacts, relative impacts associated with waves, that kind of thing. That'll probably be further out, maybe a year from now or so.
So just to make sure, I think, Colin, you're asking about policy and regulations.
Well,
Okay.
that was that part. I was curious when we would actually have something where, when I go to Bachelor, I can talk more confidently about what we think we know.
Yep.
And there is a part of our project where folks from ecology are involved, and they're thinking, they're not currently thinking about changing regulations, but they are at least thinking about changing the guidance for example, if you're updating your SMP.
Yeah, so that's,
King County is also part of this project.
right, King County is part of this project, but part of it is focused on the guidance document for the Shoreline Master Planning that Ecology publishes.
And is that intended to be out prior to the, say, Tri-County area having to actually turn in their SMPs in June of 2019?
I do not know.
That's a good idea.
Yeah. Yeah, I haven't heard them. There's a draft that they've circulated. I haven't heard yet a
I think
timeline.
actually it's pretty close.
It's pretty close, yeah,
So
but
I think it's going to be early 2018.
yeah. Was there a question?
Well, I had a question about the island maps. By the way, thank you for coming over.
Yeah, absolutely. Thanks for having me.
Is there something done for the Puget Sound area, meaning the shoreline all the way down to Burien level? Is it something to be just
In terms of mapping?
yeah, of the map you showed?
No. So, so as part of this resilience grant where we're doing this kind of like these updated projections, we don't have any mapping capacity. For these kind of localized projects, we have done mapping, and the examples that I showed are pulled from those. So we don't have any sort of concrete plans yet to provide any kind of regional mapping. We've talked about different options. I mean, certainly one thing at the basic level is you can translate some of this projection information to a first order vulnerability assessment using something like the sea level, NOAA's sea level rise viewer, or some of these other mapping tools that are out there. There's a whole variety of them. So that's kind of a first order way you can do that. And certainly, a lot of communities and jurisdictions have GIS expertise in-house in which this kind of information would be fairly easily translatable. Yeah. Was there a question? No. Okay. Yeah.
Not that we don't have enough to worry about.
Yeah.
With sea level rise impacting properties and
Yeah.
structures. But I'm wondering, has there been, what the extent of research there's been on, say, other impacts associated with sea level rise? I'm thinking of impacts on habitats,
Yep.
water quality, particularly locally. Or is that just dwarfed by the noise and insignificant compared to other anthropogenic impacts? Just thinking as an agency, we worry besides sea level rise impacting structures, water quality
Yeah.
concerns, habitat concerns.
Yeah.
And maybe this does make a difference at a micro or local level. I'm just wondering if you're aware of that type of research or.
I know it's out there. We're not going to summarize it here. There have been various efforts to try to get at, sea level rise impacts on, salt marshes, for example, in Washington State. There have been certainly questions posed about things like influences on eelgrass beds. I haven't seen an actual sort of rigorous analysis of the potential impacts, but I know people are sort of thinking about it and talking about it. Anybody else know of any sort of specific habitat-focused assessments? Laura's saying yes.
Yeah, USGS did a really good one for Padilla Bay. No, not Padilla Bay, it's Wallace Delta. So there are those kinds of assessments available. They're very location specific. So there was one attempt by the National Wildlife Federation back in 2007 to do a comprehensive assessment of changes in habitat associated with sea level rise for much of Puget Sound, parts of the outer coast. It's very out of date. So the more updated kind of studies are very site specific because of the intense effort that's required to model those.
So it's something that we're definitely looking at. So actually, one thing to mention is more on the planning project end. Department of Ecology's Toxics programs just put out, I think, a set of guidelines or
Yep.
guidance for if you're managing a cleanup site, how to start thinking about climate change, sort of step by step in different cases. So there's definitely an interest in looking at it, and a big part of, Ian mentioned that we're doing the sort of science piece of this larger Washington Coastal Resilience Project, but the bulk of that project is really how do you use the information, and that kind of question has been coming up a lot in all sorts of different contexts. So one example is we're working with the city of Tacoma. It's one of the pilot communities in that project, and they're doing a sub-area plan for the port. And I imagine that that's going to be a big question as part of that.
Right.
I think we're getting kicked out of the room, so.
All right. Thank you.